Hello guys, welcome to the 12th class of this course. In the last few classes, we talked about the Lagrange's equations of motion. We saw some applications of that, and we saw how from the D'Alembert's principle, we can derive this Lagrange's equation of motion. So the D'Alembert's principle was basically a differential principle. Now, we will use an integral principle to derive this uh, Lagrange's equation. So what do I mean when I say integral principle? So let's first define that. So this Hamilton's principle, which we will talk about, is a integral principle. So integral principle is like using this principle, we can derive the Lagrange's equation of motion where we need to consider the entire motion of the system between times t1 and t2, or t initial and t final. And small variations of this uh, small variations of this motion from the actual one. So in an integral principle, so let's say there is a particle that, so it's a space, let's say it's a space of the generalized coordinates. So we have P1, we have P2, then we can have P3, we can have P4, etc. So at time T1, the particle was at position at here, and at time T2, the particle was at this point. So let's say this is the actual motion. So so to use an integral principle, we need to consider the entire path the particle it traces while going from T1 to T2, from this point to this point, and we need to vary this path. Okay, so this is the actual path, and then we need to vary this path, and then after that we will use some principles which we call the Hamilton's principle to derive the Lagrange's equation of motion. So that's the whole idea of an integral principle. So where we consider the entire motion from this initial point to final point, and this entire motion we uh, use the small variations of that to derive the Lagrange's equation from the Hamilton's principle. So that's the idea of integral principle. Now, now let's define a few things first. So let's define a configuration space. So configuration space is a space spanned by the generalized coordinates. So we can have a lot of generalized coordinates, P1, P2, P3, Pn. Okay. And these all are perpendicular. So in 3D, it's impossible to draw more than three. In this plane, it is impossible to draw more than actually two coordinate properly. So if we have, let's say, if we have only two generalized coordinates, in that case, the configuration space will look like this. It's P1 and P2. But if we have three coordinates, we can still draw something uh, like that. So P1, P2, P3. But beyond that, we cannot really draw in this plane actually. So a configuration space is the space we consider a space which is spanned by the generalized coordinates. So this is not the usual 3D space because generalized coordinates, they are not necessarily the Cartesian coordinate always. So a configuration space is not, the well the 3D space you can easily visualize the Cartesian with Cartesian coordinates. Now, as let's say a particle is at point at time t1, it's here at this point. So now as time goes on, what particle will do? It will, as time goes on, its coordinate will change, or it will remain stationary if the particle is stationary in configuration space. So in general, we can say like the particle moves from T1 to T2. So at time T2, the particle is here. So as time goes on, then the system moves in the configuration space. Generally speaking, the system moves in the configuration space. And it traces a curve in the space. This curve traced by the particle or the system in configuration space is called the path of motion of the system. So remember that this path of motion of the system, which you are calling the curve traced in the configuration space, it is not um, in general the path of the particle that we see in 3D. Okay, so in 3D, a particle, the path we can see of a motion of a particle, that is not necessarily be the same path in the configuration space, because the configuration space, in configuration space, the coordinates are not the same. This p1, p2, p3, this can be angles, this can be anything. So these are not always the Cartesian coordinates. So in general, this path of motion of the system is not uh, what we visually see while the particle moves in time. Now let's define another thing, which is monogenic system. So it is defined like a system where all the forces except the forces of constraint can be derived from a generalized scalar potential that may be a function of position, velocity, or time. So the potential, the scalar potential, that can be a function of anything like position, velocity, or time. It can be a function of anything. So if the scalar potential is only a function of position, then the monogenic system is called a conservative system. So to get a conservative system, the potential that must be a function of only position. So if we have the position, we can define a potential. Or basically, if we have the change of position, we can easily from that information only we can say the potential difference created. So with these definitions in mind, let's define the Hamilton's principle. So what is the motivation here? So what we are trying to get? So we are trying to get the actual, so there can be a lot of different ways a particle can go from this point, so from this point to this point, right, in configuration space, let's say. So we are trying to um, define a principle which will guide us to identify the correct path which a particle will follow while going from this point to this point. So that's the idea behind introducing this new Hamilton's principle. So let's define this. Hamilton's principle for monogenic systems. So it is applicable for monogenic systems, not, I mean, not only for conservative system. Principle is the motion of the system. So the motion of the system, when I say the motion, I mean the motion in configuration space. The motion of the system from time t1 to time t2 is such that the line integral I, so this is the line integral from t1 to t2 L dt has a stationary value for the actual path of motion, where this AL is the Lagrangian, which means T minus V, kinetic energy minus potential energy. So this line integral I, this, so this is the Hamilton's principle. It says the motion of the system. So if we find the actual path, and then you so along the actual path we do this integral from t1 to t2 L dt. So this line integral, it will have a stationary value. Okay. So what do we mean by a stationary value? How do we define it? So we'll define it very soon. So let's first discuss about this line integral. So this line integral I equals to t1 to t2 L dt is called the action or action integral. So then the Hamilton's principle says basically the motion of the system from time t1 to t2 is such that the action has a stationary value for the actual path of motion. So now what do we mean by the stationary value? So let's understand that. So let's say this is a configuration space. So it's a configuration space. So Q1, Q2, and a particle. This is the actual path from T1 to T2. In configuration space, this is the actual motion of the particle. So this is the actual path. Now along this path, if we calculate this line integral L dt, so and then if we vary this path a little bit, infinitesimally vary this path, not the position of the particle, we are varying this entire motion, path of motion. So then we will see that this line integral, it has a stationary value. That means it is not really changing. It's kind of at its extremum, local extremum. So this means that this delta of I, which basically is delta of point T1 to T2 of Lagrangian dt. So Lagrangian, it can be a function of generalized coordinate, generalized velocity, and time dt, it equals to 0. This action or this action integral, it is not changing its value if we infinitesimally shift the motion, the path of motion. That's the meaning of stationary value. At this path, at this actual path of motion, the value of this integral is stationary. By infinitesimally shifting this path, the integral, it will not change. So this is the statement of Hamilton's principle. So after defining Hamilton's principle, we will move towards the calculus of variations. We will see that's how this Hamilton's principle, using this Hamilton's principle, we can achieve the equation of motion of this actual path. Let's say we have a function. So let's say we are in a one-dimensional configuration space where the coordinate is or the generalized coordinate y, which is a function of time. Now, let's say so this y, it is kind of defines the path. So this y defines the path defines the path of a particle or a system along the space. Now let's say we have a function if, which is a function of y comma y dot means dy dt t, and we have an integral along the path yt from t1 to t2. So let's say we have a function and we have an integral along the path. So we have an integral along the path such that the integral j is defined like from t1 to t2 f of y comma y dot comma t dt. This f is kind of the Lagrangian here in this Hamilton's principle. Okay, and this j is kind of the action integral. We can call it as treat it as action. So we will propose that for the actual path, if y is the actual path, if y is the actual path of motion, then j will have a stationary value. So this is the kind of idea behind for this Hamilton's principle. So let's say, so then this is not the configuration space. So at time t, if we say what will be the value of it, so how y will vary. So it can take this path, it can take some different, it can go from here to here, from this point to this point, or some different way. So if so, then let's define a parameter alpha. So it's a parameter that defines the path of the system. So if we choose a different path, then alpha will change. So that's how alpha defines a new path. So then y is basically the path. It can be any path. The particle can go from this point to this point. Okay. So in that case, y will be a function of t and alpha, which is equal to t comma 0. This is the actual path plus alpha eta x. This alpha is the alpha tends to 0. If we consider this y t alpha is infinitesimal variation from actual path. Okay. So, and this eta t. And this eta, it can be any arbitrary differentiable function. So this yt0 for alpha equal to 0, we are proposing that we will get the actual path. The parameter is defined in such a way. So in that case, if we need to vary this actual path infinitesimally small, if we need to vary this path, then we will change this alpha. So this alpha will slightly change and this eta is any arbitrary function. So in this way, the path, the actual path, we can vary. So then this condition on eta is, eta at t equal to t1 equal to eta at t equal to t2 equals to 0. This is simply because at t equal to t1, this initial point that is same. So we are starting from a particular point and we are ending at a point. So in that case, it for the actual path or for any infinitesimally varied path, these 2 points, so y at t0 and y at t alpha, these two will be same. So in that case, this eta t, it should go to 0 at these 2 points. That's the condition we have on eta. So now let's vary this path, vary this path, and let's look at the variation of this action integral, that is j. So the variation of this action integral. So first define this action integral. So we already defined it. J, it is from t1 to t2, y, it is a function of f, which is the analogous to the Lagrangian f of y. Y is the path, which is a function of t alpha, comma y dot, which is a function of t alpha, comma t dt. So now the variation of this line integral with respect to alpha, which is di d alpha. That means if you vary the path. it is dd alpha of from T1 to T2 y T alpha y dot T alpha dt. Now this alpha is independent of T, so we can take this derivative, this dd alpha inside. So in that case, from T1 to T2, dd alpha of f, and f is a function of y and y dot, which are functions of alpha. So in that case, by chain rule, we can have plus del f del y dot del alpha dt. So now consider this second integral. What we have is from T1 to T2 del f del y dot del alpha dt is equals to from T1 to T2 del f del y dot del 2 y dot del alpha del t dt. Not y dot, it's y. Y dot means del y del t. Y dot means del y del t. Because alpha is not a function of time. So y dot means dy dt, where y is a function of t and alpha. But alpha is an arbitrary parameter. So it has no dependence on t. So d alpha dt, that is 0. So in that case, this dy dt and del y del t, partial derivative with respect to t, that will be the same. So we can write this y dot as del y del t. And there is also another partial derivative with respect to alpha, del alpha. So that's why we have, it's a second order derivative. So del 2y del alpha del t. From T1 to T2, del f del y dot del t of, so partial derivative we can interchange dt. Now if we use the integral by parts, we will get del f so we will get del f del y dot integration of this, integration of T1 to T2 del t of del y del alpha dt. So the limit will be in the entire expression T1 to T2 plus integration from T1 to T2. This integral will be del y, okay. First this derivative, so it will be ddt of del f del y dot, and then this integral will be del y del alpha dt. Now this term, it will be del f del y dot times del y del alpha from T1 to T2 plus from T1 to T2 we will have ddt of del f del y dot del y del alpha dt. What is this del y del alpha? Now look at this definition of y, how we define the any path. So del y del alpha. So if we do this del y del alpha, there is no alpha dependency here. So del y del alpha will be eta t. And what is the condition on eta? At T1, eta is 0. At T2, eta is 0. So in that case, del y del alpha is basically, we can write it as eta t. And if we put the limits, then it will be 0. So in that case, the second term in the integral will become from T1 to T2 ddt of del f del y dot del y del alpha dt. Now we will put this term, this integral here, this value at the expression of this j del j del dj d alpha. So in that case, then dj d alpha, it will be integration from T1 to T2. Okay, I did one mistake here. That is, in the partial derivative, we will have a minus sign. Okay, so this first function intact and then integration of that, and then derivative of this first function and then integration and dt. So there will be a minus sign in between. That's how the partial derivative, partial integration is done. Sorry, it's partial integration. So then there will be a minus sign. So in that case, the minus sign will be here. Sorry. In that case, we will have this del f del y minus ddt of del f del y dot, and we can take this del y del alpha common. So we have dj d alpha, the rate of change of this action integral with respect to the path, if we vary the path. So alpha is the path parameter, you can say. So that is given by this term. Okay. So now if we use the Hamilton's principle for this problem, so the Hamilton principle says that if we have the actual path, so if we vary our alpha around our actual path, then this j, this action integral, it will have a stationary value. The rate of change of action integral, it will be 0, right? That's the meaning of stationary value, it will not change. So in that case, so according to Hamilton's principle, if we have the actual path, then the variation of j with respect to alpha variation of j with respect to alpha around this path is 0. So that means dj d alpha around actual path equals to 0. It means integration from t1 to t2 f of del f del y. So yes, del f del y minus ddt of del f del y dot del y del alpha around actual path dt equals to 0. Now, what is del y del alpha around this actual path? If we look at the expression of y again, so this is the expression of y, and del y del alpha around the actual path, it will be eta, right? This eta t. That means t1, t2, del f del y minus ddt of del f del y eta t dt equals to 0. Now this eta t, it can be any function, it can be any arbitrary function. It can be any arbitrary function. So in that case, if the integral is 0 and eta can vary as we wish, as it wish. So in that case, this term must be 0. If this is not 0, so then integral will not be 0 if we change eta without any restriction, without any condition. So eta can vary. It's a free arbitrary parameter, and in that case, this term inside this integral, it must be 0 to get the entire integral 0 for all values of eta. Then del f del y minus ddt of del f del y dot must be 0. Or we can write ddt of del f del y dot minus del f del y equals to 0. So J for action can have stationary value only if the Lagrangian which is f here satisfies this equation. And you can see easily, like this is a Lagrangian equation of motion if we treat f as Lagrangian. We will do that in next class. But before that, we will see some applications of this Hamilton's principle. There are a lot of applications, a lot of beautiful applications of this calculus of variations. So we will do that, and then we will introduce the Lagrange's equation of motion with this variational principle. And let's define another thing, which is like the virtual displacement. Uh, Here what we have is del y del alpha around the actual path, and the virtual displacement is basically given by delta y, which is this del y del alpha along this actual path times d alpha. This is how a virtual displacement is defined. So in that case, we can write like, so from this equation, so we can write like delta y, it is basically this integral times delta alpha. So t1 to t2 del f del y minus d dt of del f del y dot del y del alpha along actual path delta alpha dt now equals to t1 to t2 del f del y minus d dt of del f del y dot. This term is defined as delta y, virtual displacement, times dt. So and so this is not delta y, this is delta g, the variation of action. So by using Hamilton's principle, we can write it like delta j equals to t1 to t2 del f del y minus d dt del f del y dot delta y dt. Let's see. This is the condition we have on this action integral. That is variation of this and action integral, variation of this action with respect to the actual path. From the actual path, it will be zero, infinitesimal variation. That means the action is stationary along this actual path. Okay, so that's all for today. So today we discussed about the Hamilton's principle. We defined what is configuration space. We defined this integral principle. We defined configuration space. We defined the monogenic systems, system where the potential can be a function of position, velocity, and time. And we defined the Hamilton's principle, which is applicable for any kind of monogenic systems. And there we learned that the action integral. So if we have the actual path in the configuration space of our system, then the variation of this action or action integral, that will be zero. So the action is stationary around the actual path. and this gives us this equation of motion. Okay, this is the equation of motion. So if this equation is satisfied, only then we will get this J, the action, it will have a stationary value along the actual path. Okay, so this is what we discussed today. In the next class, we will talk about we will see some application of this Hamilton's principle, of this variational principle. So these are very interesting applications we will see. Okay, bye.